So yeah, I'm Bryan Reed. I'm with IDES or IDES or EDES or really however you want to say it. I say IDES. And we are a wholly owned subsidiary of Joel. But I'm the CTO. I get to do what I want, so I act like an academic. So I'm formatting this like a research talk and not a sales talk. So there are actually quite a few people that contributed to the results in this. This is the core team currently at IDES that contributed primarily to what I'm going to show. But we have lots of co-authors, lots of collaborators. I have an acknowledgement slide at the end for that. So let's get into it. So why do you want to use electrostatics in a TEM? And the answer is speed, primarily. So TEM normally uses magnetostatic lenses and deflectors. So they are very stable. You can focus strongly. They have low aberration, easy vacuum engineering. Why are they stable? Because they're intrinsically low pass filters. Right? You've got these coils that the current does not want to change. That's what inductance is all about. So that, on the other hand, that means they're slow. It can take many microseconds or milliseconds to settle, and they have hysteresis, they have drift, right? They're magnetic systems. The things can heat up, things can move around, and it's not that great. If you just add a few electrostatic components in select locations, you can get a lot of flexibility. So they can be much, much faster. They can operate on the nanosecond scale rather than the microsecond or millisecond scale like the magnetic systems do. They have basically no hysteresis if you do good circuit design. And depending on where you put them, you can do quite a few things. But the vacuum engineering is trickier because magnetic fields go right on through, brass beam tubes like they're not even there. But electric fields, not so much. You have to build those into the vacuum. That's right, there I have them. So there are a bunch of places that you could put an electrostatic system added to a microscope. So the accelerating stack is already an electrostatic system. You can add a fast deflector as a beam blanker. You can add fast scan plates, or you can add a deflector after the sample. It's funny, Angus, like capturing this because he already has most of the stuff on his microscope. I'm happy to share the slides with you later, Angus. So to use any of these effectively, you need high-speed digital timing control. To take advantage of the fact that you can do stuff in nanoseconds, you better have a control system that can coordinate these things on the nanosecond scale. So good system integration and a concept of what you actually want to achieve. So yeah, you can add cool components, but you want to actually think about how you're going to use them, and that can get complicated. So let's start at the top of the column. So playing with the accelerating voltage, you can shift the voltage to do a fast focal series quickly. So shifting the accelerating voltage. So this is a slide of stuff that we are doing in collaboration with Joel in Akashima. So this is a fast focal series, 8 frames captured in 2 seconds, completely automated. This is the slow version that uses the objective lens current. So you have to wait for that to settle. But the same hardware, and I realized I don't actually have the data to put on a slide, unfortunately, but it works. The same hardware can electrostatically shift the accelerating voltage for every single frame. And we can synchronize that with our fast beam blanker, which we call EDM, and get rid of transient effects, get rid of rolling readout artifacts on the camera, so that each image that you get is a pure defocus with no blur, no rolling readout crap, none of that. So that's fun. I don't want to spend too much time on that because it's like, it is what it is, but it connects to some previous talks that we've seen. Scan plates. So I'm putting this near the top also because we're not doing it yet, but we sure would like to. So normally you do a stem scan with magnetic deflectors, and they're very slow, and they have problems, and they have time constants. They have multiple time constants, and wouldn't you like to replace those? So yeah, if you want to do quantitative stem work, I strongly advise putting the lower half of the column into real space imaging mode and taking a picture of what the scan actually looks like, and it may be very eye-opening. So this, I went to a very small scan, so it's easy to see what it's doing. So this is an 8 by 16 pixel scan. I did it rectangularly, so I was certain which direction was horizontal, which was vertical. And at 100 microseconds, you can see that the thing is stopping on each pixel, and there's only a little bit of streaking in between. But boy, the streak, when it flies back, it jumps and it flies and it overshoots. And I'm actually going to use it over here. I don't like the way this thing is drawing. So it overshoots and then flies back. Well, it actually overshoots quite a lot. So the contrast that I have on this image is appropriate for this 100 microsecond dwell time. You reduce the dwell time to 8 microseconds, and yeah, it's not moving and jump and settling on each spot. It's not fast enough to do that. It is continuously moving, and each pixel is a superposition of locations, really. And when it tries to fly back, so here we're blanking the beam except when it's actually measuring. Here I have a 2:1 aspect ratio rectangle with square corners. Does that scan look undistorted to you? It doesn't look undistorted to me, especially this first line. This one's nuts. So if you invert the polarity on the beam blanker so that you're only seeing the flyback, woo, baby, it's doing some crazy stuff, especially on the flyback at the end of a scan. This is not a first order differential equation. This is at least second order. It has momentum. It overshoots. And the time constants are in tens of microseconds or more, or hundreds of microseconds to fully settle. And at short dwell time, it doesn't really step, it ramps. And the scan is distorted and shifted. If you change the dwell time, you're not looking at the same locations. So if you want to, so that the take-home messages from this is conventional raster scans with long flyback times are the standard solution to get around this. So there's a reason that they go to the left end, establish momentum, and then start collecting data. But all the time, they're blowing up your sample, right? The beam is not turning off conventionally. So doing that again and again for every scan line. So that's how you get undistorted scans conventionally. Now, if you want to use unconventional scans where you're moving in, an arbitrary pattern, you had better calibrate this stuff or you will not know where your beam is. And either way, at short dwell times, the beam is in multiple locations, and the positions of the pixels depends on the dwell time. But synchronizing with a fast beam blanker can help a lot in a couple of different ways. One is simply by eliminating the flyback dose. So you turn off the beam while you're not collecting data, because if you've got a fast beam blanker, why on earth wouldn't you, right? And you can also eliminate pixel-to-pixel transients, especially with arbitrary scan patterns. So instead of having this crazy-looking thing where, to get to A to B, you have to go to New Jersey and back, right? You're sitting in one spot settled, you blank the beam, send the command to the deflector to move, wait for it to settle, unblank the beam, and then as far as the sample is concerned, you have teleported the electron beam from one place to another with nothing in between. So, yeah.
I have this question. Why do you have to scan this way? Why don't you scan this way?
If you scan zigzag, you get a different time lag for the odd rows and the even rows, and you need to correct for that. Yeah, so people are doing that kind of thing. That's one of the non-conventional scans, but you have to calibrate to know where the beam is in that case. So yeah, that's a good question. So yeah, it's roughly a linear system. So the overshoot is proportional to the jump, right? I mean, it's really being set primarily by RLC time constants. Using small auxiliary scan coils can actually make it like 10 times faster. So you can have a major coil and a minor coil. I'm not showing results from that, but the folks in Akashima have done some pretty cool stuff with that. That's actually already published. And the long-term solution is to switch to electrostatics when you want to scan faster in arbitrary patterns, because those can just go, instantly fast on the time scale of the kinds of experiments that you're usually going to do. All right, so now we're talking about electrostatic dose modulation. That's just what we call this fast beam blanker that we put between the accelerator and the first condenser lens. So it's a pair of plates that we can drive voltages plus on one side, minus on the other, so that we're driving it into a fixed aperture quickly. And We can do it with a transient of just a few nanoseconds and a settling time of a few tens of nanoseconds. So we quote this as a 50 nanosecond switching time. That's being conservative. If you're not worried about the settling time, if it's like that's good enough alignment for me, it actually switches in less than 10 nanoseconds. So if you use it, so this is explaining magnetic beam blankers are not good. So this is using our electrostatic stub framing system, which I'm going to describe a little further. But we're subdividing a camera into a 4x4 array of smaller frames using a fast deflector between the last electron lens and the camera. And we can switch discretely between states nice and cleanly and get these 15 images at 12 milliseconds each. But the first image, oh my God, what happened to that, right? Well, it looks like nasty astigmatism. Well, it is astigmatism, but it's not from misfocus of the lenses. It's from the fact that the beam is tilted. It's like third order aberration coefficient kind of astigmatism. The beam is tilted, so you get an astigmatism in the image. That's because for a large fraction, that 12 milliseconds, that beam is settling and stopping and partially blanked and badly aligned. So you get these bad-looking images at very short exposure times based on the magnetic beam blanker. So milliseconds is crazily slow. I mean, but we can switch in tens of nanoseconds. So being able to do that is a vast increase in the beam blanking speed, and it gives you a lot of room to play tricks for how you're going to use that. So the reason that people don't normally blank the beam during the flyback is because the magnetic beam blanker is too slow. It's like if I have 500 microsecond flyback time and it takes 10 milliseconds to blank and unblank the beam, that's just not even an option. But if you've got 10 to the 5th speed increase in your beam blanker, then you can do that kind of thing. So you can do on-the-fly dose control without affecting imaging conditions. I'll show you that in a bit. And we can use pulse width modulation then on a microsecond scale and change the effective intensity of the beam without affecting focus, without affecting alignment with this really quite simple system. So the user interface for this is intended to just make it easy to do what you want to do. So there's a simple GUI that lets you enter in numbers and select them on settings, but that GUI can be externally controlled with a REST API, so you can automate stuff. We've got a little knob that lets you just adjust the beam current. And for people that don't do STEM, just the ability to adjust the beam current up and down without changing anything else is like, oh my God, that's please. It's a surprisingly basic capability that's actually very, very hard to do normally. Because if you change the beam current in a conventional way, you're like refocusing lenses, changing apertures, refocusing something, and oh God, I just spent 10 minutes getting my aberration corrector all set up, and now I need to redo that. And we can also take external input. So if you have any high-speed timing control system, you can control the beam blanker directly. So in TEM mode, this is just showing adjusting that pulse width modulation, and it doesn't always project very well, but if you look at the Fourier transforms of these, you can see that like the spots are still there. They're just, of course, the signal noise ratio is down because you're looking for less time. So it's like 50%, 10% duty cycle. The information's all there. Signal to noise ratio is down, so it's not affecting focus or alignment. And it's even more clear in the stem at very high magnification. So in each one of these pixels, we are turning on and off the beam an average of 9.5 times. And even at this crazy high magnification showing silicon dumbbells, we're not seeing distortion, we're not seeing backlash, we're not seeing hysteresis, we're not seeing anything at all. So when I say we can, this electrostatic deflection allows you to adjust the beam current by an order of magnitude or more without affecting focus and alignment. This is what I'm referring to. So once you can do that, you can start doing other things. So the simple thing, as I mentioned before, is just to blank during the flyback. So you can synchronize with the scan system and just listen to the timing signals that are coming from the scan controller and just blank the beam when you're not actually collecting any data. And depending on your parameters, up to like half of your time can be useless flyback time. And depending on what scan controller you're using, during the flyback, it might be parking the electron beam right at the left edge of the sample, depositing heat, depositing mobile charge, creating mobile ions that might be doing all kinds of mischief. And I don't know if you've noticed, but typically the left side of the sample is the one that radiation damages first in STEM. And that's why. So if you just set up, so this is a real space image of the scan and how you're dosing the sample normally, so with and without this blanker turned on. And here it's just like ideally what you would draw, and here it's just ugly, and it goes over here and it settles and it comes back and it bounces back and forth for a while and then it starts taking data. So these are equivalent dose. This is on strontium titanate EDX scans, and we're damaging the sample a whole lot when we're not blanking the beam during the flyback, but really much less when we're blanking the beam during the flyback. So that's fun. So dose is not the same as damage. So here I'm showing a result that I'm pulling from the literature, and if you saw Nigel Browning's talk, come on.
Right, yes, a quick question. So you are able to synchronize exactly the flyback. So once it goes to the end on the right-hand side, the flanker comes in.
Flanker comes on. Yeah.
And then I assume because when you change the magnification, then the scanning constraint is going to change, and then the flyback and the momentum on the left-hand side is going to be different. Is that correct? So you will have to characterize that a priori in the microscope.
But in our case, as long as you've set that, so if you're doing a conventional scan, we're just listening to when it's actually collecting data. So if they've set up the conventional scan so that so the flyback is all good and done, and you've established momentum and are in a nice, uniform lag.
So the timing it is that, and the collection, that is your clock.
Yes, yeah, exactly. We're basing it on the clock of the STEM controller. So we're not paying attention to the deflection signals which have, unknown lag. We're assuming that the STEM controller has been set up well to compensate for those problems that I showed a few slides back. And if so, then we rely on the timing signal from the STEM controller to say what's real scan time, what is not. So as I said, there's more than one group that's doing this kind of work, and the consensus is that how you apply the dose matters. So damage per electron is a quantity to think about optimizing, and if you do a conventional raster scan, pixel by pixel by pixel by pixel, you are depositing stuff. Could be free radicals, could be heat, whatever. It depends on the time scale you're talking about. But on the time scale of a typical STEM scan, it's probably like mobile radicals and charged atoms and things like ions and whatever. So you're depositing that stuff and they're diffusing, and there's going to be like a nonlinear threshold effect where the damage is just worse, much worse. And in fact, this work, which came out of Joe Verbeek's group, actually showed that it's actually modeled quite well, the simple diffusion plus threshold model. So you scan conventionally, and you're just pushing, the propensity for damage forward as you move on, and just accumulating, and you're going to mess up the sample a whole lot more. But if you jump in like a checkerboard pattern, interlaced, however you want to call it, so skip over and give the sample time to chill, you could still hit every pixel, just hit them in an unconventional order. And with the newer vector scan controllers, you can program this stuff very nicely. Then same dose, much less damage. You're still damaging, right? But this can reduce the damage per electron by a factor of 2 or 3, or maybe a bit more than that in the sorts of things that have been published. And the scale of the diffusion constant that we're talking about is a few nanometers squared per second. So that's not heat. That is not mobile electrons. That's something else. Now, there are other experiments on picosecond scales that show a similar kind of thing that almost certainly are using different mechanisms. But yeah, this is an active area of research. There's actually a bunch of groups that are looking at this kind of thing. So, okay, so you've got this fast beam blanker. Wouldn't it be nice to be able to program it to do cool stuff? And sorry, I'm just borrowing this slide directly from another thing, but it does describe what it is. So this is a little box that has an FPGA and an ARM processor in it, and it has a highly programmable digital pattern generator inside, and it can be programmed to listen to all of the timing signals from a scan controller and control the dose modulator pulse width modulation on every single pixel in the scan independently. So if your scan controller is putting out like a vertical blank signal, a horizontal blank signal, and a pixel clock, then our system listens to all those timing signals. It goes, aha, I'm in scan line 12, pixel 85. The user wanted 60% dose on this one. I'm going to turn on for 60% of the pixel dwell time and then turn off. So as a result, you can get this kind of crazy thing. I think Angus actually walked in the room while I was capturing this image. This was done at RFI. This is one of our prototype systems, and so just doing a normal STEM image of just like your normal kind of nanoparticles, right, on the substrate, defocused a little bit so you get high contrast because we're just showing what it can do, and I drew this little digital image. It's a 4K by 4K image where got a grayscale image, got grayscale logos, got this single pixel fractal thing with checkerboard, grayscale modulated from left to right, and just imparted that onto the scan. So this image in the middle is what came off the scan detectors, right? This is an unprocessed image. So really it's just a stunt to show, yeah, we can do dose control in every single pixel. So, and if you zoom in on it, we have single pixel precision. So we can say, I want 5% dose in this pixel, none in this pixel, 85% in this pixel. Yeah, question.
So in these images that you're taking, is there sometimes problems of dynamic range that you're exceeding the dynamic range with a normal scale to use a constant modulation, so to say?
No, not really. I mean, so you adjust the detectors so they're not saturating at 100% duty cycle, and then you're fine as long as you have enough beam current that at the lowest duty cycle you're still getting significant signal. But I mean, that's just a general problem of.
Yeah, so the question would be if like the overall dynamic range would be too large for your digitization, you could use the local modulation to sort of.
I see what you're asking. We can program it to have up to 12 bits of grayscale, but the pattern generator operates on a 10 nanosecond clock, right? So unless your dwell time is at least 41 microseconds, you're not getting all of those bits of grayscale modulation. But if you calculate the expectation value and the square root of the expectation value, right, the noise and the number of electrons you're depositing, 12 bits is actually kind of overkill. It's not really very significantly different at that scale. So thanks. So usually operate at 8 bits, it can go up to 12. So how would you want to use this? Well, we do it in what we call dose painting mode. So you can scan and see where you want to. So someone could scan this device, right, and say, ooh, I want to put no dose up here. I want to do like 50% dose here and 100% dose here. And you just draw on it and say where you want to do it. Or you get your computer to do it. So there's an open API for automation. You can plug any algorithm into the dose painter feedback loop. I'm actually going to skip through the rest of that slide. So what could you do with such a system? Well, if you saw Christoph Koch's talk, you probably can already imagine a few things that you could do with such a system. But this is just a computational study of a 4D stem in a sort of orientation imaging microscopy mode, and you're just putting dose where you want to and figuring out where the information is, and preferentially looking at the spots where the information is and reconstructing in a more dose-efficient way the information that you actually want, and avoiding the damage from depositing energy into the areas that you don't care about. All right, so finally I'm going to talk about the deflector after the projector lens and before the camera. So this is, we call it relativity. It's because it does time compression, but it allows you to raster multiple images across a large camera for time resolution. So the idea is actually pretty simple, but the way you use it ends up being interesting. So you just put a high-speed two-dimensional deflector there, but it's a discrete deflector that jumps among a bunch of discrete positions and selects among, I draw it as a 4x4 array. We can do anything from 2x2 to 16x16. So you can just subdivide the time, the exposure time of the camera, into 16 and just expose them in sequence. But you can also expose them completely out of sequence, jumping around and around and around and returning to the same position multiple times, which ends up implementing a compressive sensing matrix. So you are mixing each one of these images, each one of these 16 subframes is now a superposition of different points in time with known coefficients. So if your underlying data stream is highly compressible, you should be able to reconstruct not 16 frames from this, but say 100 frames from that. So that's the trick of compressive sensing video that we're using. So yeah, the subframing system, this just shows it in a little bit more graphic detail. So yeah, you can step through. But a fun trick that we can play is to get rid of rolling readout artifacts on a camera. So a lot of these microscope cameras, especially the ones that are doing a continuous readout, they're lying to you a little bit when they give you a sequence of frames and say that this is this span of time and this frame is this span of time, and it's like, yeah, the timing offset is different for every row in that image. So if you Google rolling shutter artifacts, you can find like crazy looking Picasso propeller blades, and it's just nuts what this can do. But it mixes different points in time in a complicated way. But if we run our deflector so we are never exposing where it's reading out, and if our reconstruction software knows that we are operating in this mode, we can reconstruct continuous video with one of these things with no rolling readout artifacts. So that's fun. Let's see. And there's actually quite a bit of signal in a high brightness electron beam. So this is 19,200 frame per second atomic resolution. Not very many pixels in one image, not great atomic resolution, but I mean, it is what it is. You can get that. And we're not sure how far down the limit is. So yeah, that's fun. So this is unprocessed. That's what's coming straight off the camera, and we can do this continuously. We just synchronize, and this is not using compressive sensing. If you notice that a lot of these frames are partially overlapped. We're trying to make the most use of the camera. With using compressive sensing reconstruction algorithms, we can get that data back. It's tricky, and it's hard to get the tools into the hands of users just because of how tricky the analysis is. But if you have a good forward model of exactly the displacement and distortion that your deflector produces, and you know you've calibrated the noise in the camera and so forth, you can formulate this as a compressive sensing problem and disambiguate which of the features in the overlap regions belong to which subframe. So if you do this analysis, this is the same data before and after this overlap correction. And if you look close, you can see there are still some artifacts. But I mean, it does a pretty good job, I think. Yeah.
It does look good. One question in the overlap areas where it's jumping back and forth,
Yeah.
could you instead just use the most recent available frame for a prediction of what it should look like? to get this?
I can do that, and a variant in the algorithm allows me to do that. But I prefer to only show stuff that I have direct knowledge of rather than interpolating.
Does your software extract this or export this mask too? You could do this yourself as a user if you had that.
You could. You absolutely could. Right now, the software that does this is a bunch of cobbled together MATLAB code that only I know how to run. But I mean, it works. It works. It's tricky, but it works. So yeah, the original camera had 4 megapixels. This reconstruction has 5.1 megapixels of actual data. I'm not counting what I'm showing as black. So, you know, that's data compression. It's a small compression ratio, but it's data compression, and it's recoverable. So here's an example of using the overlap resolution. Oh, in fact, this is exactly what you just asked. So this is an option in the data. I forgot that I had done this in this one. The pointer is not doing. So anyway, the pointer is decidedly not. You know what? I'm going to give up on it. Oh, there it goes. So yeah. So this is 15 frames of pulse laser melting and de-wetting of nano gold, and so I did drift correction and denoising and overlap resolution on this one. And the denoising is kind of interesting. So I'm just doing total variation denoising, but it's 3-dimensional total variation denoising. So it's looking at the frames immediately before and after to help it decide whether some feature is real or not. And I'm also calibrating the noise in the camera. So I'm setting chi-square per pixel to be, I think I set it to 1 on this one. So it's saying, don't change the things too much. Only get rid of features that are consistent with being noise, right? And I've calibrated the noise. So you can see if you look at this, if you compare the left image with the center image, then it is getting rid of a lot of like clearly meaningless speckle, and it's getting rid of some motion blur features because it's comparing the frames immediately before and after. So that's fun. Yeah, I'm pretty happy with that. It's not like over smoothing, it's not under smoothing because we've actually calibrated the noise, and we're doing that. So let's see. I'm trying to pace to cover everything I want to pace without rushing too much. So conceptual answer example of the compressive sensing video. So as I said, we jump around multiple positions repeatedly. So during one exposure of the camera, so this is a typical kind of image that you would want to capture in an electron microscope. And during one exposure of the camera, our subframing system is jumping around and accumulating dose. And we're getting all these different kinds of images, and you know the frog's doing his happy thing. And then at the end of one frame, we read this out. This is one camera frame. It has 16 different superpositions. Now, if you look at this, they're all quite different from each other. And if you look, you can see, you know, you've got a frog sitting here, and you've got a frog sitting here, and like half a frog sitting there, and you could imagine a computer looking at that and going, what is the simplest description of a sequence of events consistent with this stuff? So it's like scrambling the information, but not like scrambling it too much. So you have some hope of recovering it, and the computer looks at that and uses some sparsity assumption. And in this audience, I'm not going to go into too much detail on that. It's like either you know or you don't. But basically, assume the user isn't trying to take a video of pure random noise. And you know the measurement matrix, which is just this piano roll kind of thing. You know the thing you measured on the camera, and you have these sparsity assumptions, and you get the image back. So this is not actual TEM data. So no frogs were injured in this measurement. So an example with real data. So this is on a system at Sandia National Laboratory, and this is using a camera that is capable of maybe 1 hertz acquisition. So we captured this. I did a little bit of pre-processing. I actually dropped the first frame where the beam blanker was doing its ugly thing, as I showed early on, but that's a minor complication. So this is pulse laser sintering of a cluster of gold nanoparticles. And we've got the superposition of a whole bunch of different points in time. We've got 15 different superpositions. And I make a model of 100 consecutive time steps. And I have a model of what that should look like on the camera, given everything that I know about the distortion, the deflection, the superposition on the camera, the piano roll matrix, and all of that. And I compare using my calibrated noise metric. And I iterate and iterate using total variation to regularize this otherwise underdetermined linear system of equations. And that's actually it. That's like all I did. There's a whole lot of details involved in getting that to work well, but mathematically it's not that complicated. And at the end, what you get is that little video in the lower left corner and with selected frames up here. So I deliberately didn't turn the laser on until sometime into the video because it's a check on the reliability of the reconstruction, right? So if I had seen it respond to the laser before I knew I turned the laser on, I'd know that that was an artifact and that I was trying to pull more time resolution out of it than was actually inherently in the data set. But here in this video, I mean, you could see there's quite a bit of detail here. So you can see that the outer surface melted. You can see that there's still some crystallographic contrast in the inner parts. So the inner parts didn't fully melt. It sintered nicely. You can see when most of the sintering happened. So the laser was on the whole time, but the absorption goes down as it sinters because the plasmonic hotspots go away. So it's sort of a self-limiting process. This is the process that's involved in a lot of pulse laser 3D printing. And we're here watching it in detail on the multi-millisecond scale, multi-microsecond scale, really. And we're doing it on a camera that can't even take 1 frame per second, just because we've compressively put all of this data into one camera frame. So so how far can we go with this thing? So we ran out the same kind of experiment, this time on nanocrystalline gold and just coarsening it. And this time it was at 10,000 frames per second reconstruction. And it's noisy, and here we are not getting perfect time resolution. Like each individual reconstructed frame is not really independent, but we can see this process, and we can see it in quite a bit of detail, and then take an exposure at the end and see that it actually is reconstructing real stuff. So that's fun. Let's see. So that's the end of talking about the experimental results. Now I want to talk more about why this stuff works. Right. So I'm going to talk about information theory and Shannon entropy. And this is going to connect with talks that you've already seen in this workshop. So I'm actually really happy that Christoph went before I did, because he provided perfect examples of some of the stuff that I want to talk about. So you have a probability distribution, and you just want the negative expectation value of the log of the probability, and it turns out that this is a really nice property that we can call entropy. It's similar to thermodynamic entropy in some ways. It's a measure of the unpredictability of a random variable. It's basically how many numbers could you expect to come out of this thing? How unpredictable is the outcome of the thing? Irrespective of how they're sorted, right? So this one and this one might have the same entropy because they have the same ensemble of probabilities. It doesn't matter how they're ordered. And a really narrow peak has low entropy. So it sort of generalizes the concept of a width of the distribution in a way that is independent of any ordering of the data. It's just the ensemble of probabilities. I'm ignoring a difference between entropy and differential entropies for people who are familiar with the theory. There's an important technical distinction, but I'm not going to get into it in this talk. So I think of microscopy as information theory, right? So there's stuff you want to learn, and there's information you can get, and what is the best way to do that? So if we think of it in terms of entropy, the a priori entropy about the sample, call it S, is this cloud, and it's like all the stuff you don't know about your sample. And you want to know some fraction of it. And then you get some information from a measurement, and there's going to be some probability distribution of numbers that could come off your measurement. And there's an entropy associated with that probability distribution. So you have an H of M and you have an H of S, the a priori information about the sample. So you do a measurement, and now some of this information is actually about your sample, and some of the information is just noise. So there's some entropy where even if you knew everything about the sample, there's still some randomness in the measurement, just because you're sending some finite number of electrons at the thing, and you have some detection probability and, Poisson statistics and drift and whatever, right? So that's not interesting, but this little yellow kind of teardrop shape is what's left, and this is information about your sample. So that gets plugged directly into this thing. So now the entropy of the sample, the stuff you don't know about your sample, is reduced by precisely the measure of this yellow teardrop. So it turns out that this HS minus HS given M is equal to H of M minus H of M given S. That's a standard result in information theory. So the a posteriori entropy about the sample is what you still don't know about that. So what you want to do is make this yellow blob and put it in a good place, right? So what you don't know is reduced by exactly the amount you learn, which we call the mutual information, which I said there's actually many equivalent ways to represent this. It's actually easy to prove this theorem. Well, you do start out knowing something about your sample. So there's everything there is to know about your sample, and then there's what you know beforehand, your a priori knowledge. How do you want to encode that? Maybe you just want to encode it as the images that come off it actually look like something, right? They don't look like pure random noise. They got a low total variation. They're compressible in some dictionary, whatever. Or maybe you're assuming it's made out of atoms in three-dimensional positions with certain scattering factors associated with them and so forth. And then there's the stuff that you don't know about your sample, and then there's what you want to learn about the sample, and then there's a big part of the blob that's like you don't really even care. So you think about what you're doing with this measurement. Some fraction of the information that comes in about the thing is actually about your sample and not just about how you rolled the dice in a sampling of a Poisson distribution. And if you put that yellow teardrop here, you're wasting your time. Like, ooh, you learned a whole bunch of stuff that you don't care about, right? If you put that teardrop here, it's like, well, you got a superposition of stuff you don't care about and stuff you already knew. Do that if you want to calibrate your detectors or whatever, but you're not getting anywhere. This is more like it, right? So yeah, you're learning some stuff you don't care about, inevitably, you always will, but you're learning a good chunk of what you want to know, and there's a bit of overlap with the a priori stuff, so you can actually verify at least a bit that your a priori assumptions are reasonable, right? So kind of in between is where you want to be optimally. So after you've done this measurement, this information that you've gained is now a priori knowledge for the next measurement. And ideally, you should redo this calculation, redesign your measurement, put the teardrop of the new measurement onto the stuff that you still don't know and want to know, and iterate. And that is what we call adaptive sampling. So let's see, by my count, I've got 7 minutes left. Okay. Cool. I think I'm actually going to finish a little early. So the lessons from this are everything there is to know about your sample is here, and everything you get from the measurements. So measurements should be targeted in proportion to the likelihood that you'll be relevantly surprised. So if you can predict what the measurement would give you, plus or minus not very much, you're not learning much from it. If you can't predict what you did from your measurement, but that's just because there's noise in the measurement, you're not learning much from it. but you want to not be able to predict your measurement specifically because of something interesting about your sample. So you want to target the information appropriately. A priori knowledge should inform your interpretation of data. So if you pretend that this little light blue oval doesn't exist, and your a priori assumption is your image is white noise, you're not actually optimally using the information. So there are these wonderful denoising algorithms that work surprisingly well. Even a very simple one, just total variation denoising, works surprisingly well, and is really pretty blind. It works over a huge range of images. So that should inform your interpretation of data. If you want to make the most use of the information per electron, you should be using this at least a bit. A priori knowledge should also inform your capture of data. So using compressive sensing or adaptive sensing, since as you learn, you should adjust your strategy, and you should avoid verification of things you already know. You don't want to overexpose, don't want to oversample, don't want to overconcentrate. If you've only looked at 5% of the pixels in an image, where should you send the next marginal electron? You should send it to the pixel you know nothing about, which is almost certainly one you haven't looked at yet. And that applies in the limit. Most published TEM and STEM images are likely massively oversampled or overexposed with respect to their true information content. That, to me, is really the lesson of the fact that these undersampling in painting things still provide pretty good-looking images. So people want to show a nice-looking image, but the fact is they could have learned enough to answer their hypothesis with some tiny fraction of how much they nuked the sample. And on the other hand, you need to have enough redundancy to be confident. Your a priori knowledge might be wrong. There have to be enough checks in your system to, actually I might not, I might not have a huge amount of time left. So anyway, and you need quantitative statistical models to do any of this. So real world data is highly compressible. So not just like 95%, but 99.9999 whole bunch of 9% of mathematically possible images look like absolutely nothing. So the mathematical constraint of it actually looks like something reduces you down to an astronomically tiny sample of the possible images that you could capture, and that's why compressive sensing and denoising and stuff have any chance of working at all. If you just look at it as straight, an unconstrained linear algebra problem, it's hopeless, it's underconstrained, what are you going to do? But these regularization tricks really work really well. And the data that comes off 4D STEM is enormously compressible. I'm actually not going to go into detail on that because it's already been talked about a bit. So to apply the math, it's actually surprisingly simple. A lot of compressive sensing problems are formulated something like this, give or take, like I'm sure Peter knows 1,000 variations, but looks something like minimizing some one norm of some matrix operating on your model such that you might have a non-negativity constraint. In electron microscope image, you usually do, such that the forward model of what you measured is within noise consistent with your measurement. And that's actually all there is to that. I've got a lot of extra text on this slide, but you look at the YouTube video, you can read it. So it's very important to calibrate the noise if you want to do this quantitatively. So what does this mean, this little simple matrix thing, 2 norm less than or equal to epsilon, where you work it out and you scale by the error in each parameter. You can scale each row in the matrix, and you can scale each measurement by the measurement noise in that. And what do you know? This is chi-square. This is the classic chi-square from statistical data analysis, and you know what its distribution should be if you have calibrated the noise correctly. So I strongly support the idea of calibrating the noise in your detector in detail before doing any of this stuff. So you're not just like turning the knob on the denoising until it looks good to you. You want to have an objective way of setting the denoising so that it's like it is consistent with the noise level you expect. The noise you remove should be consistent with the noise level you expect from your calibration. And by the way, every TEM detector of any kind that I have ever calibrated the noise on follows an equation like this. So the variance is a dark variance, the noise that you get even when there's no signal, plus a constant times the intensity. This is a term that scales as Poisson noise. In terms of the theory, it might as well be Poisson noise. So I just often call it that. And almost the entire useful range of the measurement, this linear term dominates. So speaking informally, almost all TEM measurements are dominated by Poisson noise pretty much all the time. It's not quite 100% true, but as a rule of thumb, it's a good place to start. I've already kind of gone over this conceptually, and I'm running out of time. And anyway, the audience is pretty familiar with this stuff. But Poisson noise messes with the theory of compressive sensing in a pretty bad way. So there's this nice old result from Roginski et al. From 2010, and you put performance bounds when the limitation is Poisson noise as opposed to additive Gaussian noise, and it's much, much worse. It's much, much worse. Compressive sensing does not like Poisson noise. I mean, you can still do it, but you have to be careful and do it properly. And I'm also going to skip through that. But the key point is diminishing returns of information. So with any kinds of these things, if you're looking at the information return per electron, there's a lot of different mathematical models that give qualitatively the same thing. The information return per electron decreases on a sort of logarithmic curve. So it's diminishing returns. So if you've already measured some variable by throwing 100 electrons at it, throwing another 100 electrons at it is going to give you a small increment of additional information. So think carefully about how you want to target your dose and where you want to put it, especially thinking about the dose mechanisms, the spatial temporal depends of the dose damage mechanisms. Dose is not damage. So finally, the takeaway message is a few electrostatic elements in select locations give you speed, flexibility, and control. And there's clever stuff you can do with them. I call them clever tricks. So I think that's a lot of fun. Ideally, every electron should tell you something you don't already know. Otherwise, why are you using it, right? Don't dose when you're not recording. Don't over-verify values you could confidently predict from current information. A little redundancy, though, is still good. Otherwise, you could fool yourself. So if you're barely able to extract a reconstruction, you maybe don't trust it. Give yourself enough redundancy to know, like where I took a bunch of images where nothing is happening before the laser turned on. That kind of thing. So it's like, yeah, okay, I could have measured dynamics in those time scales, but I didn't. I wanted to know that I could believe the result. How you apply the dose matters. Give the sample a chance to chill. The data analysis algorithms associated with the compressive sensing help you make the best use of available info, even if you don't use compressive sensing. They're very nice algorithms, like just TV doing denoising in particular is fast, easy, surprisingly effective. There are variants of it that are optimized for different kinds of things. I strongly recommend looking into that kind of thing. Compressive sensing itself is not magic, but maybe an appropriate choice when you're limited by data throughput primarily, but not so much when you're up against the signal-to-noise ratio limit if you're dominated by Poisson noise. So the classic theory of compressive sensing is about reducing the number of numbers you need to get a certain data set, not reducing the number of electrons you need to throw at a sample to get what you want to get. And it turns out they're very, very different things. Calibrate the noise in your detector if you want to do quantitative work, and adaptive sampling and AI-driven microscopy are huge and promising frontiers, but I don't need to tell you that. So just put up my acknowledgement slides, and thank you for your attention.